So today I'm going to talk about entry production and especially the fluctuations away from the mean and how that can tell us about dynamical phases in active matter. And here's just a little picture of, I guess, one of the main features of active matter that is really, I guess, the question that makes this interesting is if you set, self-propelled particles in a system that's dense enough with no attractions between these particles, then they'll phase separate just because they're self-propelled. And so this is, I guess, a simple example of a non-equilibrium system where you get phase separation with no attractions explicitly in your model. And this here is just colored by the density. So this is, or nearest neighbors, same thing. So the blue is like really dense and this is like dilute. But I guess the question is, can entry production tell us anything about phase separation, other models? And I would say that right now I'm at Princeton in the physics department, part of the Center for the Physics of Biological Function and the Princeton Center for Theoretical Science. But this work is largely based on my PhD work. I got my PhD last year. And so, yeah, so this is still new, even though I'm not at Berkeley anymore. So just a little bit of motivation. I mean, I know I probably don't need to motivate you all. You probably have seen this many times, but some examples that we see are, this is in Scotland, the starlings. You see all of this collective behavior. They're moving around. There's shocks and stuff going on. I guess it's like the quintessential idea of active matter. Another one is in Africa, the Serengeti. You see these wildebeest; they'll flock together. Yeah. So this talk I gave this talk at another workshop in South Africa, and so this is kind of like why it's kind of shifted this way. But the idea is there's a lot of going on here. There's a lot of collective motion. I'm not claiming that I'm going to tell you how this works or like the physics of it, but I guess to motivate saying, well, maybe there's some fundamental features in these very complicated realistic models that show up in these very simplified models that I'll talk to you about today. So I guess a model that's more close to home is this synthetic colloids, where if you turn blue light on, they'll become self-propelled because the blue light signals a chemical reaction, and they start producing hydrogen peroxide and dioxide and they start making gradients, and then they become phoretic and active, and so they become self-propelled when the blue light. And if you turn the blue light off, then they become just equilibrium colloids. And so this was one of the first, I guess, synthetic colloid examples where this clearly demonstrating that the self-propulsion can lead to phase separation and interesting non-equilibrium phases. And since, so I guess this is more close to what I might talk to you about in a second. And since then, I guess in non-equilibrium systems in general, what can we say about them, I guess, is the question. We rely so much on equilibrium stat mech, but really none of that really applies, and it'd be kind of silly to try to use them in cases where it's clearly a non-equilibrium system from the single particle level. But there are some things that have helped us understand entry production. One is a fluctuation theorem. So one of the main ones about entry production specifically was the Crookes fluctuation theorem back in 1999, which tells you that the probability of observing, this is the probability distribution, so observing some plus s value of entry production divided by the probability of observing the negative of the same s is equal to e to the s. And so it's just a relationship that tells you about the fluctuations of entry production. Also, a little bit more recently, entry production is also fundamental in telling you about just currents in general of non-equilibrium system or any system, but non-equilibrium system because obviously it's trivial if this is zero. But this is just telling that for any current, it could be mass current, charge current, whatever current you have in your system, it can be constrained by the entry production, or it gives you a bound on the it gives you a bound on the fluctuations of that current, for the, which is given by the entry production. So these are two, there's more, but these are just two examples where fluctuations within the entry production tell you something about the system. S is like the average, or like, so here S is like a value of the entry production of the system. Yeah. Yeah, it should be, so this would be average. This one would be average. Yeah, I should have put average there, yeah. And this, one thing to note, that if you put S, if your current that you look at is the entry production, then this just gives you back a Gaussian distribution. So that's just something to remember. Okay, so now this is just a little bit of background. Also, I guess, what I'll use to study entry production is large deviation theory, and it's just the way I look at it is it's just a tool, a set of tools that allow you to make predictions about probability distributions in the same way that equilibrium StatMech does, and in fact, this is just in some way a generalization of equilibrium StatMech. But it's not as powerful because you don't have clear connections to pressure and entropy and so forth. But you take a trajectory in phase space, say C is like a configuration. So from a trajectory, this framework will just allow you to get a probability distribution. Here is I want S, and it just assumes that the fluctuations are exponentially decaying. And here it's extensive in time and system size with number of particles. But in practice, what I'll do is, and I think this is what's done usually, is they get this cumulative generating function, which is like a free energy, because you take derivatives with lambda and you get cumulants, just how you take derivatives with beta and get cumulants of the energy. Except this is now a path ensemble, average over paths. You can get this guy by just solving an eigenvalue equation, and the largest eigenvalue gives you the cumulative generating function, and then that's how you can get back to the probability distribution by Legendre transform. And then a little bit later, you can also, and these are just some references, there's many more, and a lot of them are experts in this room that I've read. These are just some specific ones that I've benefited from. And here you can say optimal control force, where if you solve all this spectrum problem, this eigenspectrum problem, then you can actually then get a control force that will allow you to add that to your original dynamics and give you interesting dynamics that maybe phase separation, for instance, or other interesting dynamical phases. So these are all tools that I'm going to use, but like I said, I probably don't need to spend too much time on that because you all are experts on this already. So I guess really quick, why even study entropy reduction? I guess one reason is, well, it's a metric of how far you are from equilibrium. If it's 0, you know it's the equilibrium system. Another one is that, which I'll be talking about, is it provides a thermodynamic picture of phase separation and other dynamical phases. And I mean, it's not, but then another question is, well, why do we care? Like, what can you do with the entropy reduction? Well, I won't talk about this, but it can allow you to do useful work, such as with active heat engines, or what some of you talked about, where you could do work by pushing a rotor and so forth. So this does have a thermodynamic connection to other things, but I'm not going to focus on those. I'm just going to focus on this, which is first, I'm going to give you a bound on entropy reduction in active matter for a wide class of models, and then what we'll see is that this bound will be not as general as the one I showed you before, but it will be more, because it has more details about active matter, it'll be a tighter bound. It'll be better in some cases. And we can actually interpret when those deviations from the bound, what they have a physical interpretation, mainly that they'll be dynamical phase transitions, and then we can study those as well. And then I'll show control forces that give rise to some of these dynamical phases. Okay. So the model that I study, the general class of models, will be of this form, where this is just a Langevin equation. It's overdamped, so this is for the ith particle in your system. And this first term is just the self-repulsion, where the v is just the magnitude, and the bi is the direction. And I'll tell you, for different models, the statistics of this b will be different, and I'll tell you them in a second. This is just excluded volume, so there's no attractions in any of the models that I'll consider. And then this is just diffusion, so it's just Gaussian white noise. Eta is Gaussian white noise in x and y, and yeah, and d is just the diffusion constant. And so the models that I'll consider, there are several of them. The first one is active Brownian particles and run-and-tumble particles. So for that, this orientation vector bi is just cosine theta in x and sine theta in y, and the statistics of theta will depend for active Brownian particles. The statistics of theta is diffusive as well, in a different dimension, and then the positions. And for run-and-tumbles, as mentioned with a lot of the other models, earlier, is that there's some rate at it's ballistic, or there's some rate that it tumbles with some gamma or characteristic time scale. But they still have the same form. It's just the statistics of theta is different. So then active dumbbell particles is really similar, except here the noise comes from the fluctuations in the two particles. The Brownian fluctuation in the position of the two particles gives rise to noise in the orientation, which is kind of similar to active Brownian particles in a way that it's diffusive, but it's different, diffusion. And then lastly, I'll consider active Ornstein-Uhlenbeck particles, which here, this is probably the most different out of the models considered, because this, if you do v times b, both the magnitude and the direction can change. So it's not a constant speed on average. It just, it can fluctuate, and the orientation changes. Okay, so these are the models that I'll consider, and specifically for the entropy production, how we compute this is it's the log ratio of tau, or gamma, sorry. Gamma is like the phase space variables, R and B for all capital N particles in your system. And then you just take the log of the forward probability from like 1 point in phase space to one at your end time. And then what's the probability of taking that in reverse, which is this gamma tilde. And that's what we use. And there was there's been a lot of work, which I'll highlight in a bit, about, should this term be even or odd under time reversal? And it really depends on like the actual system you want to study. So right now, it doesn't, you really could be either one, because it depends on the actual system you want to study. But if you don't consider those specific details, you're welcome to pick either one. But the good news is that it doesn't really matter which one you pick, because the interesting behavior is the dot product between the self-propulsion and the force, which both will have. Both, it doesn't matter the convention. Just the one that I have will have a non-interacting contribution as well. Uh-oh. AD. Here? Oh, active dumbbell particle. Yeah, okay. Yeah. And so when you do this convention, the form that you get is sometimes called the active work. So it's just the work that's done by the self-propulsion in the direction of motion. Okay, so that's what we'll study. And then we'll study the intensive version, where it's scaled by system size and time. Yeah, so this is just conservative interaction. Yeah, coming from a potential. Yeah, so this is the only, in red is the non-equilibrium part. Okay, so one of the main results that we did is, well, you can just rewrite that cumulative generating function I talked about a couple of slides ago, just write it as a path integral. And then what you could do is you could do a reweighting of the path probability where it's reweighted by an arbitrary force u lambda. So u lambda is a force that you would just add to that original equation of motion, and that would generate a new path probability. And so right now it's general, it could be anything. But if you pick the right one, the one that realizes fluctuations that are proportional to lambda, then this will be better. You don't need as many trajectories to get this average. But right now it's just an arbitrary u of lambda. And so then when you take Jensen's inequality, you get now a bound where it has two terms, and then when you plug in the definitions, you get this form. So it's not trivial to get here, but for all the four models that I showed you, it's of this form, and there's two terms. The first one is just the non-interacting part. So this is just the free particle contribution, and I'll show you what those forms are. For some of them, for the AOOPs, it's non-trivial and very non-Gaussian, and it's interesting. And the other ones have interesting forms, but maybe more intuitive. And the second term is just so this is an ensemble average with a control force u of lambda, which I'll tell you about before. But this control force for this bound, it's the control force that when you solve the eigenvalue equation for the non-interacting particles, it's that control force that realizes the fluctuations of the non-interacting particle. So it's a perturbative correction where you run dynamics with the non-interacting potential and take this average to get the first order correction for interactions. And beta here is just the inverse temperature. And what it ends up being is that for a mean field, it's just a friction term, meaning that I think this should be minus. But what it does is that it just slows the particles down. So in mean field, it just slows the v down. You're not going to go v. On average, you're not going to go v because there's particles in the way. It'll slow you down. And so this is like a mean field way of looking at it. It's just a friction term here that depends on lambda. And so this form is only true for the active Brownian particles, active dome-built particles, and run-tumble particles. But yeah, this is just an idea. Okay, so now I want to show you the results of this bound and that versus or compared to like the actual dynamics. So yeah. Yeah. So it's just an extra term. So you would add that to the Langevin. Yeah, you could compute. Yeah. How's the u of lambda? Yeah. So it's just where's the large deviation theory part? So it's just so you would find this potential, and then you would take a derivative with respect to. So this will depend on like your phase space variables, and you take a derivative with respect to that phase space variables to get the force u of like little u of lambda. So it's from solving the eigenvalue equation, eigenspectrum, and then the largest one, take the log of it, then that'll give you a force that you can add to the. It's just yeah. Okay. Oh yeah, okay. Yeah, tilting, yeah. Okay. Okay. So for AOOPs, I'll call them AOOPs. So this is the form, what it looks like for the non-interacting. So we were able to solve it exactly by solving that eigenvalue equation. This is the largest eigenvalue. And what you see, and here are the results for three different magnitudes of the self-propulsion and three different densities. So these are all, so at the average, these are all, they're not phase separated, but if you would, there are deviations, they're hard to see over here, but it's because the scale is so large, but there are deviations over here from phase separation, and there's slight deviations over here from another phase collectively moving. It's hard to see on this one, but I'll show you in the other one. But the idea here is that this is not gonna be a Gaussian. This is not a Gaussian. So, but we can, and then we correct for the interactions by that form I showed you before with the friction. Yeah. 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 So this. No. There's only one right choice, and it's directly given by the largest eigenvector, yeah. So from the largest eigenvector, you take the negative log of that eigenvector, and then a derivative with respect to a position, and then you'll get this force. So there's only one if you do it, when you solve it. But there are people who are in the game, like Rob Jack and others, who will try to use physical intuition to think what might be a force that would realize those fluctuations. But they'll always be like very inaccurate because these need to be exponentially correct, precise. Okay, and so for the AOOPS, it has a different. So for the AOOPS, there's this correction, there's this force, but there's also another force contribution that changes the. So this would go into the position, and there's another one for AOOPS that would go into the orientation one, but I'm not showing that one. And then for active Brownian particles and the other models, you see that there are the deviations, although they are the same as AOOPS, it's more clear to see. So here, this red line is the bound, and so if you are small, so it's not, and this is very rare too because this is on n divided by n and t. But the idea is that really only for small self-propulsion you see bound, but if you go rare enough, even the one, v equals 1 will deviate, and there'll be phase separation or something, other phases. But as you increase self-propulsion, it becomes more, even worse. And we're scaling it by this quantity here to show deviations from the bound, which is almost Gaussian. And if you scale these by, if you plot it as the actual rate function, which are the point symbols, as a function of the bound, you see that, for the right-hand side, that's these points. Well, the blacks are always there, but the black points, and then the blue is this side, and then the phase separation side does not do well on the bound at all. But why does it deviate? Well, the answer is that those are dynamical phase transitions. So, and I'll show you about that. Oh, and these points are obtained by importance sampling. So we use cloning. So I use supercomputer to do cloning, and so you can get these rare tails. And yeah, so now let's investigate both of these sides and see what that looks like. So first, so if you take from that I of s, that rate function that I just showed you, you can take for a specific value. So this is for v equals 120, the largest one. That was this one here. Sorry, the large one. But now it's a different color, so sorry. So here we're taking this, and I'm just plotting. So before I was just plotting this little range here, but now I'm plotting the whole range, and you can see that it has the structure of Maxwell construction, because we're doing, so I'm finding the cumulative generating function, I'm getting the rate function, so that's why there is the Maxwell construction. And here, and like I said, we can get the average by doing this quantity. So because I know I of s and psi of lambda, I can take this average. And what we see is that it has the behavior of a first order phase transition in this weird space where at lambda, so starting from here, going to the left, there's a sharp jump to a phase that's almost zero, or to a phase that's -1 on this scale. And as you increase n, it gets sharper and sharper, and over here that's like you're approaching some phase that's going to be equal probability. So this is telling you like, this is here I'm implying that in the limit that n goes to infinity and t goes to infinity in the right limits, that you would get something where it's equally probable to be in the like a dense phase or this dilute phase. And these are snapshots from important sampling. Cloning is very hard to do with more particles than this. Even this is hard, but you know, there's better methods now. But yeah, so this is what this phase looks like. This is what this phase looks like. And so this is, like I said, this looks like a first order phase transition. And there's others have tried to quantify this more further since then. Okay, so the other thing that we could do is, well, so the other thing I can do is we can write optimal control of phase separation. So to do this, we write a diffuse. So first, it's in k-space. So we convert. So from the continuity equation for the density, we kind of use it as a starting point to get like a fluctuating density form for the system, but we're treating it as diffusive at this limit. Obviously, I think doing optimal control, considering not only the density, but also the orientation, like the polarization, that would be very interesting, but it's also not possible, I think, at this point. But yeah, that would be very interesting. So here, this is just a diffusive model where this d of lambda kind of contains the self-propulsion in it as just correcting the diffusion from Brownian motion. And this is just a term that's the noise for the density. And this is all in k-space. And then so this is all to understand phase separation, but to do that, I need to have some positional information. So that's why I'm keep doing this in k-space. Okay, so here we can also write, I'm calling this delta W because this is the contribution of the active work that is the interaction part. So it's the VB times the force. But here, so when you write that out, it'll give you this, but we're not using the theta. So we're only using, so we're saying like the dot product is exactly 1, or -1 in this case. And so we're losing information because we're just looking on head-on collisions pretty much. But this is what it would look like. And so now what we can do is you can solve the so I can create another eigenvalue equation now in this fluctuating density variable. And this is your observable. And you can solve this eigenvalue equation. And now it's a sum over k space. And what you see is that this is what you get and I'm calling delta psi because it's like a correction to the mean field one that I got before due to phase separation. And what you see is that this becomes non-analytic at a certain point, which is this value. And here I'm just looking at k equals 0, I think of this. But here you see that there's a critical lambda predicted here for phase separation that scaled as 1 over v and also 1 over n. And this is in like the long field limit. That's why it's like k equals 0, because it's like a long, long wavelength. And then here is like a phase diagram that's like a 1 over n scaling. So it's just saying that as you increase v, if the phase separation is over here and homogeneous over here, the closer the closer that you get in n, or the higher v or higher n, this goes closer to 0 to where it's more likely to phase separation. Eventually you'll phase separate at lambda equals 0. And then what we can do is under, in the most, I guess, simple form, you also can get the eigenvalue, the eigenvector, and solve for it. And what you get is that you get something that is that negative lambda, which is lower than average, gives rise to long-range attractions. So, and in a very rough way, this tells you how phase separation occurs by lowering entry. So lower than average, this is saying that lower than average entry production, this is the force that they approximately feel for phase separation. So this tells us how there's approximate attractions here. You're right. So this would technically, yeah, this is on the homogeneous side, but we're hoping that the critical point from the homogeneous side tells you something about when this becomes not analytic. Ah, I see. So you're saying like, how do I know it's like uniquely a phase separation, not something else? I mean, well, so we haven't found any other phase transitions, but it's possible. I think Rob, Jack, and others found that there might be. No, it's not on this side. I think on the other side there might be an hyper uniform phase as well, but I think it's on the other side. Yeah. Okay. So that's all for the phase separation part. Were there any questions on that or any? Yeah. Yeah. You're saying like just the physics of it, or what in this function? Just the physics. Yeah, yeah. So well, I'll show you what they feel. I'll tell you what the particles feel. So yeah. So here, so before the phase transition, they're all just sort of happy doing. It's just homogeneous. They're just doing their own thing. They bump. But then what happens is that there's correlations that are induced with the excluded volume and the vectors, such that now they somehow become correlated to like this, and they get crowded, and then so they're all pointing towards each other. Huh. The rate function. Yeah, the rate function. It's so it's like approaching this side. So it's like you start here. So we start here. This is our state, and then you start. Yeah, this is your starting point here. So that's like the average behavior. So I'm saying like we're going to approach from the left the phase transition. No. There's fluctuations. There's fluctuations. So it's not what all that we're seeing here is not stable for. It's just like a fluctuation. It's saying that if I set up a system here that's like this, if I wait a very long time, what will I see in the tails of that distribution? It is, but the rate function tells you all the information about the fluctuations as well. Mm. Ah, so well, I mean, so like V and everything is fixed, but you're saying like the effective velocity or something, like like local density or something. Well, so yeah, so how these are set up is that it's like this is fixed. So like for instance, this is just like so this is just a number. This is just a number for the whole plot. This is all. These are all fixed. The only thing that's changing are the fluctuations from the noise and the fluctuations in the orientation are causing collective behavior that's rare, but it's strictly from the fluctuations of the model with fixed global parameters. No, it's fixed. It's fixed. The plot is. Oh yeah, so this is where we change it. This is what we change. So here, it's all at one density. These are all at the same density, and so this is V equals 1. It's this small one, and here imagine that there's units here. Oh yeah, so here this black is like a very small v. So this is the rate function, and so this is just saying that they're fluctuating.
Does something happen at the moment when?
Yeah. What happens is that this bound on this left side has a long tail, a fat tail. Yeah, so I of S. So this is not the bound. So I of S has a fat tail, which is yeah. Yeah. So like in this plot, it would without phase separation, this part would be right here. It would be just very skinny. I wouldn't have to go. But this other thing is from the other phase. So this is exactly. I mean, this is you could think of this as like a free energy but gotten from the Maxwell construction where you get rid of the non-convex part. And I mean, you can compute it, but yeah, I mean, there are. It's just a different. The change in eigenvalues. So. No, not I of S. What happens is that there's for this side, for the homogeneous side, there's like psi 1, and then after the phase transition, the dominant eigenvalue goes to some psi 2, which is a different psi. So when you go across that phase transition, I of S is still taking the max. It's taking one of these, but it's just a different eigenvalue. It's a different function that's giving you the one past the phase transition. Well, I mean, so you don't really see it. So it would be the same. So all you see is that I mean, so it's analytic. I mean, I can compute it, and and it has points. But I mean, I can't be for sure that that I'm not like missing a point and it's not possible. But when you take the average of S, which is like looking at pieces of this plot at specific points, you see that it eventually, yes, I guess if you take it to the all the way to n is equal to infinity, you would see that it does, at least the average becomes infinitely sharp, but it's just because this is flat and you can't take the derivative. Yeah. Right, yeah, exactly, yeah. Yeah, so it's a first order in this like lambda space, in this lambda variable, which directly tells you about the fluctuations or the tails of the deviations away from the mean, which is here. So it tells you about this distribution. Not so. When you say average, you're talking about this average, right? So yeah, so this is all rare events. So if yes, like if you looked at the steady state and you looked at it for a very long time, it was a very big system, you could see a fluctuation. It would be a fluctuation. It wouldn't be the at steady state. It would be a fluctuation from the steady state, and you would see this first order phase transition. This average, it's like average lambda. So it's a rare fluctuation. It's not like you'll see if you watch the system, like if you see it, it would just form and then it would dissipate. It wouldn't be stable. It's a fluctuation. It's rare. It's analogous to a first order phase transition because it's lambda, but lambda is not like a real parameter. It's like it tells you about the fluctuations in S. So like for instance, this plot here. So let's say this is I of S here. So at this point here, this is like lambda equals 0. This is the average. This is lambda equals 0. If I go right here, this is the critical lambda. There's a critical lambda, a unique critical lambda that's associated with a phase transition that is somewhere in between this phase and this phase. If I go even further, there's a lambda that tells you about every point on this plot. So any fluctuation within this rate function is associated with a single lambda. So it's telling you about the fluctuations. But once again, it's kind of artificial because they're working on it. People are working on it, but you can't relate lambda to a real bona fide variable like you can with the free energy, like changing the temperature or something. So it's all it's telling you about is the rare behavior and what's the type of physics, or in this case, dynamical phases, that are within the fluctuations. Yeah. No, you would never see it. But if you happen to see it, which would be very, very rare, if you happen to see it, it would be very fast, and it would just be like bloop. So it'd be like phase separation, but then it would fully, go back to this state. It would be like, yeah. So it's the lower than average. So it's like over here. Yeah. This is the homogeneous one. And that's why you have the finite size scaling, because this is the one where if I have more particles, my cluster will be bigger. It wants to be infinite. And so that's why this one grows with n. This one doesn't have any n scaling because it's converged in the particles. Yeah. This is for this is for single particles. Yeah, because the way this is just for the bound. So the way that the bound works is that you have this correction term where you use the non-interacting, the free particle force, and you just calculate this as a correlation function to get a correction. So you're computing forces with like this interacting forces with a force that's from this eigenvalue problem. So this would be exact if I had the exact U of lambda, but I don't. Yeah. Here? Wait, here? Quadratic. Yeah, it's just like a Ansager Makla path action, or however you. Huh? Yes, yeah. Yes. So this side, this side is now. So this is the exact one. This is more of like side B, like a bound on it. Huh? Yes, yeah. But here, I guess in this form, it's more of like should be like side B or something because it's not the full one. It's not the exact one. It's like a bound on it. I of S. I mean, the way I think about it is like psi of lambda. What will happen is if you go when there's a dynamical phase transition, the psi of that you would have changes. So the dominant eigenvalue changes, and when the dominant eigenvalue changes, that shows up. Yeah. So that's why the red R is the bound. But this is from simulation. So this is like our ground truth. So this has all the physics in it. I guess this is just showing how well the bound does, and then also gives us a way to interpret when it doesn't work as well. Okay. Any more questions about that? And then the phase separation is more interesting than the interesting part. Okay, so so if you go on the other side, over here, if I looked more over there, there is going to be there is a deviation on that side too, and that is related to so-called collectively moving phase. And so what happens is that, so this is that same bound here, or this is the exact points from numerics, and this is the bound. You see that it's off. And this is just a line where I fit the small fluctuations, but it's just a fit, it's not really important. But the idea here is that there's large collective fluctuations here, and then eventually they go into this, the collective fluctuations then get much smaller, and then they go into a collectively moving phase where all particles align in like one direction. So it's a spontaneous symmetry breaking, and this is a second order phase transition that has been, in the, it's not like equilibrium, but in the same way that the other one was a first order, there's a second order, there's spontaneous symmetry breaking, and they all, if this is this direction, they all go this direction. And that's a way that they can minimize interactions with each other and maximize entropy production. And this is the same average that I showed you before. From this side of the plot, you see that there's a large collective fluctuations, and eventually there's a second order phase transition here where this is that bound again, but adjusted to a different starting point. And so they just approach a non-interacting, almost like a non-interacting solution, because they're no longer interacting with each other. They're just they chose to align to maximize their entropy production. Well, because when you look at this, okay, so I guess another way of saying it is, let's see, this plot here. So this is just telling you about the fluctuations. So I guess a better way is maybe they don't have consciousness, but it's like, what is a way that they can maximize their entropy production? And by the form, there's only two parts. One is the free particle contribution minus the interactions. So the only way to maximize is to get rid of the interacting, so they don't have no interactions, because those are two competing terms. So if there's no interactions, then it's going to be the maximum you can have is just a non-interacting solution. And so then you can ask, well, what's all the ways that they can not interact? One is like, well, they could just try to avoid each other. Like they can, if this is a particle, I could stop. Huh? Yeah, exactly, and that's the collective part. That's the collective part where they're actually trying to avoid each other, and that doesn't work. And then eventually, they're like, okay, so the best way, because remember the V has to be large too. So the only way for the V on average to be its maximum is to not have to avoid it all. And so this is just, I guess, this is the physics of. So it's not what they choose. This is just what it is. It's like to have larger than average. A fluctuation that's larger than average, they'll align to maximize this. Yeah. And I guess I'll just point out that, although it's very simplified, it does kind of have some of the semblance of those Serengeti videos I showed you, where there's flocking. I mean, obviously it's not exactly the same, but this idea that, well, maybe this does have some physics that, maybe there is some overarching, physics that can tell you about active matter that shows up in many different parts of life. Yeah, and so I guess for the friction, this is an idea of how you can calculate it. You can, from the dynamics with this extra force, you can just take a correlation function, and with time, is the time step, time times a number of time steps, just a reduced time. And the idea is that, use the correlation function that will eventually converge to some long time limit, and then you can put that into your bound. And another way to think about this is through a phase, through like taking the averages with a radial distribution, 2D radial distribution function, and here it is here. And the idea is that if I tag, so at lambda equals 0, this is just on average, what will happen is that this phi here, or phi, is the relative angle between the displacement between a tagged particle and the particle that I'm interacting with, it's pairwise, and my self-propulsion. So I don't know what I did with my chalk, but the idea is that if this is like the tagged one, let's say that this is the displacement, some theta r. Let's say that this is my self-propulsion, just theta. Then this phi is just theta r minus theta, the relative angle. And so what this tells you is that as a function of r, so because they're active, this is just telling you about things that are self-propelled, that you're more likely to have density in front of you than behind you. So at phi equals 0, this thing is exactly just hitting it head on. So if this is my tagged particle, then I'm hitting stuff in front of me, and if theta is pi, I mean if phi is pi or negative pi, that's like hitting something behind the tagged particle. And that's very unlikely because they're active, you're going to hit something in front of them. But in this homogeneous phase, or this collectively moving, what you see is that this line becomes homogeneous again because they're uniformly bumping each other because they're all sort of moving at a frame that's at this V together, and they're just Brownian fluctuations within that frame, and so this is a homogeneous, it's a homogeneous plot. This is just telling you about the collectively moving phase. Okay, so that's all on the collectively moving. Is there any questions about that? Okay, well, I guess just some motivating questions, which, as I kind of alluded to already, just the question is, are there dynamical phase transitions, or are these dynamical phase transitions generic to active matter systems? I haven't showed that it's true for anything else, but a lot of the literature, a lot of the other models do have these collectively moving phases and phase separation. Well, phase separation is very generic to almost every active matter system, and so I guess is this a way to look at those phase transitions by looking at the entropy? Minimizing, maximizing. It does have a thermodynamic field to it, but it's still a little bit impractical, as these mentioned. But if you have a phase-separated system, you can measure entropy of that system, for instance, instead of starting from a homogeneous phase or something. Another thing that's kind of interesting is, as I showed, we have an approximate control force of what particles in a phase-separated state feel from a rare fluctuation. And lambda is arbitrary, but I guess the question is, and people are working on this, how can we relate lambda to a real bona fide experimentally tunable variable? It's not always the case that the fluctuations of a distribution dictate the response of a system, but there are cases where it is true. And so the idea is, well, are there forces that can actually get rid of the ambiguous nature of lambda as far as like real bona fide forces, and say like, okay, if you add this force on your system, you'll get this behavior. Then that would kind of get rid of the rareness, and it would mean that the fluctuations and all this very rare stuff that I'm seeing is actually useful. So like in this system, the light, can I relate it to light or temperature, something like that? And obviously, okay, this question, as I mentioned in the first slide, yeah, does this tell us about ecological systems? Who knows? But just food for thought. Okay, so some of the conclusions are that through large deviation theory, I can compute a bound that's specific for for a wide class of active matter systems. And as I showed, that these deviations, if you study those deviations, they're meaningful. They're not just like, oh, it breaks down. We don't know why. Well, it breaks down, and then when you study those, it's because there's actually collective behavior that give rise to phase transitions. And this was when I was a graduate student at UC Berkeley. I got my degree in physics, but I worked in chemistry with David Limmer. And this is my, I think, graduation was virtual, but we kind of took photos. Chloe Gao also graduated. Yeah, so this is me now at Princeton, still with the mask, but yeah, but I'm still passionate about active matter and large deviation theory, but I'm working on something different now. Thank you, that's all I have.